Hello everyone, my name is Kumar Aditya and in this video I will try to explain the characteristics of a thyristor. So thyristor, also known as SCR, silicon control rectifier, it is essentially a 3-terminal device, and in this example I will use this particular SCR from LTpsice. So this is the data sheet of the SCR I am using, and in the data sheet we have the symbol of the SCR. So you can see it has 3 terminal, anode, cathode and the gate terminal. And to turn on this SCR we need to forward bias it, that is your anode terminal should be positive with respect to cathode terminal, and also you need to inject a gate current into the gate terminal. So SCR are gate current control device, and to do that, to inject this current, you need some kind of gate driver. Now if this Ig is greater than a value called IGT, gate trigger current value, then your thyristor will start conducting current from anode to cathode. So this IGT value is usually mentioned in the data sheet. For this particular SCR we have IGT mentioned here. See, it's 12 to 500 microamp. Now if this current reaches a minimum value equal to IL, also called a latching current, then the gate current is no longer required. That is, you don't have to inject this gate current pulse into the gate terminal. So this thyristor will turn on fully if the current flowing through the thyristor is greater than or equal to this latching current value. So this is also mentioned in the data sheet. Now to turn off the thyristor, the process is called commutation, and there are different ways of turning off a thyristor. One would be to reverse bias the thyristor, so to make the cathode more positive with respect to anode, then thyristor can turn off. Another way would be to interrupt this current flowing through the thyristor. So momentarily, if we can force this current to 0, then this thyristor will turn off. One more way to turn off is through natural commutation. So naturally also it can turn off. Let's say the load has this characteristics due to which the current flowing through this SCR goes below IH, that is holding current value, then thyristor will turn off. Now this is the basic characteristic. Now let's see this in the Lte Spice simulation. So if I run the simulation, on the top plot I have this gate current Ig. The second plot is the current flowing through the load or through this SCR. Third plot is the voltage across the SCR, and this last plot is the input voltage. Now this V1 is my gate driver, and this voltage source is emulating the gate driver, and this 5K resistor is to limit the value of Ig. Now in the data sheet, IGT value is mentioned, right? So for this particular SCR here, EC103X1 or EC103D1, we have maximum value of IGT 12 microamp. So you can calculate the minimum value of gate resistance you need to maintain this Ig above IGT. So here I have used a 5 volt voltage source. So 5 volt divided by 12 microamp is approximately 500K. So I can pick a resistor smaller than 500K, and that will ensure that Ig flowing into this gate terminal is greater than IGT. So here I have selected 5K. Usually the maximum value of Ig is also mentioned, but in this data sheet it is not described. So I have selected it to be a 5K value, but if the value is mentioned, you can get more precise value of this gate resistor. Now you can see I have around 0.9 milliamp going into the gate terminal. So once I inject this gate terminal, this is my input voltage. This is my input voltage, and let me just change the sequence of this waveform. It's best to plot the input voltage below. So this is the input voltage and this is the output voltage. Let me pull it to, okay. And let me also plot the gate current in this last plot. So this is my input voltage, and at this particular instant I am injecting the gate current. So before this gate current pulse, this thyristor will remain off. So your thyristor is blocking the entire input voltage, right? Because current is not flowing, so voltage at this node will be same as voltage at this node. So that is what is happening here. The output is following the input. See, till here we have the output voltage. Now at this particular instant, we are injecting this gate current, so thyristor turns on. So therefore if it turns on, let's assume that it's an ideal thyristor, just for the sake of explanation. So obviously this will be a short circuit and voltage will be 0, and this is what is happening. Now this is not an ideal, so voltage is obviously slightly greater than 0, but if it was ideal, this voltage will become 0 as long as this thyristor is on. Now this is the reverse bias condition. So it's a sinusoidal signal. It goes from positive to negative, and let me zoom onto it. And when it becomes less than 0, that is, when it becomes less than 0, that means that this thyristor is reverse bias. So if it's reverse bias, it again turns off, so no current will flow, and voltage at AK will be same as Vs, right? So therefore you have the thyristor blocking the entire negative half cycle. Now in this negative half cycle also I am injecting this gate current, but this is just to illustrate you that once the thyristor is reverse bias, this no matter whether you inject gate current or not, it will turn off, it will remain off. So if a thyristor is reverse bias, this gate current has no effect on its turn on its turn on and turn off process. Now this is the current, because once we are turning on the thyristor at this interval, so once it's on, we have the current flowing through the thyristor. So I have used a pure resistive load, so current is in phase with the voltage. So similarly for the second half cycle, again I am turning on the thyristor here, so I have current flowing from this instant. I hope this is clear to you, and it may be useful to you in some kind of simulation. And in next video I will show you how you can model your own thyristor in LTspice using some discrete component and behavior voltage sources. So till then, bye bye.